Hello Biology 107 fans. So here we are with another flip lecture. Today we're going to talk about the molecules of life and how chemistry shapes biology. We've already discussed what a living being is, and for the next couple lectures what we're going to do is try and understand how the first living organism came about. And we know that that first living organism had to be able to replicate. It had hereditary material. It was able to utilize energy. It evolved. And really understanding how this came into being and what the molecules were that allowed for this first living organism is really important for understanding biology. So we know that all living organisms are made of cells. And what was that oldest common ancestor that ties us all together at the bottom of the tree of life? We have to start by understanding chemistry, and in particular atoms and the molecules that allowed for us to come into being. We are all made of atoms. We are all put together by the chemistry that holds atoms together. And how did that happen in the first place? And the hypothesis that has been put forward is called chemical evolution. And this hypothesis explains how you can take simple atoms, such as hydrogen, carbon, oxygen, and nitrogen, put them together in using chemical bonds, both covalent and non-covalent bonds, to create more complex molecules that eventually led to the first living organism. So understanding this chemical evolution and how it works is really important. Notice there's going to be a lot of things that are really important here. So where did we all begin? What started all of life? And how did even the formation of Earth happen? Well, we know that the Big Bang occurred a long time ago, and after the Big Bang there were particles that were floating around in the universe, and eventually what happened is those particles condensed. They bumped into one another, and sometimes they stuck together, sometimes they didn't. And after a few million years, shown in C here, it started the process of making planets. And the planet Earth actually evolved, notice I'm using the word in a totally different way, 4.5 billion years ago. How many is billion? Billion is 10 to the 6th years ago. So the Earth wasn't even around after the Big Bang, and it came into being. And was life there? Was life as we know it present? Probably not. So if you look at this image, what you can see in billions of years ago, the first life that evolved, came into being, occurred approximately 3.8 billion years ago. So if the Earth formed 4.7 billion years, it took approximately 1 billion years for life to begin, right? That's 10 to the 6th years. 1, 2, 3, 1, 2, 3, 10 to the 6th. Is that a billion? No, that's a million. 10 to the 6th is a million, so it must be 10 to the 9th. See, even sometimes I forget this stuff. So it's actually 10 to the 9th. A billion years ago. That's a long time for the first living organism to come about. Notice water did not begin when when the Earth was formed. And you're going to see water is really important for the ability of life to evolve. And we'll talk about that in some detail. Well, to understand this, you're going to have to understand chemistry, and not a lot of chemistry, and in particular the chemistry of 4 atoms: carbon, hydrogen, nitrogen, and oxygen. And if you look at a chart of the elements, you'll see that most of the elements are written with a number called a superscript, all right, or a subscript. So hydrogen actually happens to have both its superscript and its subscript are the number 1. And the subscript is the atomic number, and that means the number of protons. And the superscript is actually the mass, and this is, so the bottom number are the number of protons, and protons are positively charged. And the top number is actually the number of protons plus the number of neutrons. Neutrons have no charge. What are we talking about? We're talking about the parts that make up an atom. All right, if we look at this chart, you can see here's hydrogen with its superscript and its subscript, so both its mass number and its atomic number are 1. And that's because a hydrogen atom is made up of a proton, so let's just make a P in the nucleus of the atom, and all it has in addition to that is 1 electron. Now mass is made up of protons and neutrons. Electrons have virtually no mass at all, so we don't count them in the mass of elements. Let's look at another one. Let's look at oxygen. Oxygen, right, you see the bottom number is the number of protons, so that means, right, if we were going to draw this, we'd have to have 8, 1, 2, 3, 4, 5, 6, 7, 8 P's in the atom. And then, how many neutrons does it have? Well, if the number is double, 8, so that means you would have to also have neutrons in there, right? So you'd have 1, 2, 3, 4, 5, 6, 7, 8 in the nucleus of an oxygen atom. Okay, so understanding just a little bit of chemistry is going to help you understand how this biology is going to work. Well, notice I had to make some changes on this slide because I had written it incorrectly. So you know that the number of protons is the bottom number. Okay, so inside here is 1 proton, and the number of protons, if protons are positive, then we know that the number of electrons is going to equal that for each element or atom. So that means that hydrogen has 1 electron in its outer shell. Okay, shown here. And one of the things that you're going to need to know is how many electrons are in each outer shell for the main atoms. And the first shell can only hold 2 electrons. And then the next 2 shells can hold a total of 8 each. So for both hydrogen and helium, they can only have 2 electrons, but then after that, you're going to see as we start building upon these elements, there are more and more electrons in each element's outer shell. And why do we care? Well, it turns out that the number of electrons in the outer shell, it always wants to be full, to be in the most stable state. A full outer shell of electrons makes every atom really happy. So I said to you that you need to know 4 atoms. You need to know hydrogen, carbon, nitrogen, and oxygen. And that's because, notice down here, 96% of every cell on the planet Earth, every cell, every living being, 96% of it is made up of those 4 elements. 4% of every cell has other elements, and they're shown here, most of them shown with the dotted red line. So you see chlorine, sulfur, phosphorus, magnesium, sodium. Those are the other elements that make up virtually all of life. Now, there's a lot of other elements on the chart of elements. What are those elements used for? Well, they're used for non-living things, right? The rest of Earth is made up of a lot of non-living things, rocks, right? Dirt, even though a lot of dirt is actually microorganisms. So understanding the 4 main elements will take you really far in biology. The theory of chemical evolution takes into account that these 4 atoms, right, were put together in a particular way that allowed for the first living organism to come into being. So how do you take an atom and mix it with other atoms, and end up with more complex elements? Well, it turns out that in the early formation of the Earth, the conditions were really ripe for this to happen. Remember, I told you that we needed water, so when water came about on the planet Earth, that was really a critical step in the formation of these higher complex molecules from atoms, and the inhospitable environment that was going on. So there was a lot of heat and noxious chemicals were forming, and it wasn't a really nice place to be back before life began. But those particular conditions are what allowed for life to occur. So what happened was we had the interaction of atoms with one another to create compounds. Those compounds then formed together to make molecules. Molecules went together to create macromolecules, and then voila, we had a cell with some hereditary material inside of it, and that was the first living being. Voila. What does voila mean? What happened to make voila happen? If we begin to understand how these elements combine with one another, that's what's going to allow you to understand how life began. So each element, right, has a certain number of protons, and interestingly, the neutrons can change, they can vary, and if they vary, those are called isotopes. That's what we use radioactivity. Isotopes are when they have different numbers of neutrons. But for understanding biology, I want you to concentrate on electrons. Electrons are the driving force to create chemical bonds. And chemical bonds allows us to start adding elements together to make these higher ordered molecules and compounds. So remember, I said to you that you're going to need to know how many electrons fill an outer shell. And so the outer shell of an atom is called the valence shell. And valence electrons are the ones that are in that particular outer shell. So in the first shell, I told you you can only have 2 electrons, whereas in the next 2 shells you can have 8 and 8. Okay? And all of this, right, when we start to fill outer shells, what we're doing is generating chemical bonds. Here is the probably simplest diagram of what an atom looks like. You can see that in each of these, in hydrogen, you have 1 proton, whereas in carbon, how many protons? You can't really see, but you could calculate the number of protons based on the number of electrons. So there's 1, 2, 3, 4, 5. There's 6 electrons. That means that there's 6 protons. And the molecular mass of carbon is 12. So that means that it also has 6 neutrons. And how do I know that? I just know that. I remember it from the chart of the elements. And what that means is that, notice, the inner shell for carbon is filled. It has 2 electrons, but the outer shell, so the first one can have 2, but the next one should have 8. It only has 4, so this one only has 4. So how many more do we need to fill this outer shell? We need 4 more electrons to fill the outer shell, and that's going to become really important. Over here with hydrogen, right, it has 1 electron in its outer shell, so the first one can only have 2. So that means we need to add 1 more to fill this outer shell. So to make bonds, what you do is you provide atoms that can share electrons. And the sharing of electrons results in something called a covalent bond. What does that mean? Well, it means that in this image, you can see when you take 2 hydrogen atoms and link them together, okay, they get close enough together that the electrons can be shared between the 2 hydrogen atoms. Now, each of their outer shells is full, and this is actually a molecule of hydrogen gas. Okay, so these are atoms over here on the left, atoms on the left, and this is a molecule bound together with a covalent bond because the atoms are shared between the two nuclei of these atoms that are linked together. And that creates a covalent bond. Now, there are different kinds of covalent bonds. In the case of the hydrogen gas molecule, notice here they're showing you a representation of this. There is equal sharing, okay, the distance of these electrons from the nuclei. So if you pretend that this is where the proton is in the hydrogen atoms, the electrons are equidistant from the atom's nuclei for each of the atoms that are linked together. And what that means is that this is called a nonpolar covalent bond. Equal sharing creates something that's called nonpolar, and think of polar as having differences. So if you're a polar opposite of somebody, it means you're completely opposite of them. And so in this case, they're not opposite, they're exactly the same, so they're the same distance, so these are called nonpolar covalent bonds. All right, so you can have covalent nonpolar bonds. The electrons are shared equally, or you can have something completely different called a polar covalent bond. And these polar covalent bonds were critical early in life to generate additional bonding that can occur. The classic example for talking about polar covalent bonds are the bonds between the oxygen and hydrogens in water, right? So down here, what we're looking at is a molecule of water, H2O, and what happens is that oxygen actually is very stingy. It holds the electrons closer to its nuclei. So if its nuclei is here and the nuclei of the hydrogens are there, the electrons, even though they're still being shared, right, but they're closer, they're no longer equidistant, and that creates something called a polar bond. And so what we say is that this oxygen has a partial, so the delta here means a partial negative charge associated with it, whereas the hydrogens, now that the electrons are a little further away, have something that's partially positive charge. And those partial positive and negative charges are what polar covalent bonds are all about. All polar covalent bonds have partial negatives and partial positive charges. And what can you imagine can happen with positive and negative charges? Well, positives will attract negatives and negatives will attract positives. And this allows for additional interactions to occur, specifically non-covalent bonding, that is also important for the formation of molecules, macromolecules, and life. We say, all right, that oxygen is electronegative. And electronegative means that it sucks the electrons closer to its nuclei than other atoms. And there are other atoms that are also electronegative. If we look at the chart of the elements, okay, electronegative atoms hold electrons more tightly and have a partial negative charge, and that once there's a partial negative charge, that means that another atom that's associated with it is going to have a partial positive charge. And if we look at the chart, so which ones are electronegative? So oxygen is electronegative, sulfur is electronegative, fluorine and chlorine are electronegative, I think. Phosphorus is electronegative, nitrogen. So all of these have a tendency to hold the electrons closer to their nuclei than not. And that creates these partial negative charges and partial positive charges, which are going to be important for additional bonds called hydrogen bonds, which is a non-covalent bond. So I hope that explains these kinds of polar and non-covalent polar and nonpolar covalent bonds. Well, so you have covalent bonds that allow for the formation of higher order molecules, but there's also non-covalent bonds, which generate additional structure and allow for molecules to be held together. And there are 4 of them: ionic, van der Waals, hydrophobic force, and hydrogen bonding. And I'm going to talk about each of these in turn, and you really need to understand each and how they work. Ionic bonds we're going to start with, and instead of sharing electrons, this is all about giving up or gaining. So one atom is going to give up electrons and another is going to, so they're going to give it up, and another atom is going to gain electrons. In van der Waals, it has to do with how close the 2 atoms get to one another. Too close together, they repel one another. Too far away, they have no attraction, so there's an attraction, right? You need to be a certain distance between you and somebody else to be attracted to them. If they're too far away, you can't see if you really want to be attracted to them. If you're too close, it's a little scary. Hydrophobic force has to do with being not wanting to have anything to do with water, and hydrogen bonding I will discuss with you in detail. Alright, so let's talk about ionic bonds. Ionic bonds are really quite interesting because instead of, right, a covalent bond, right, the covalents share electrons, and in the case of ionic bonds, they transfer. So one atom transfers an electron completely to another atom. And the typical example for this is sodium chloride. The molecule sodium chloride is formed based on this type of bond. Sodium chloride is linked together through an ionic bond. Alright, these bonds are not as strong as covalent bonds. So if you think about a covalent bond being 2 people held together by a hand, right? We hold each other's arms together. Maybe an ionic bond would be that we were just touching one another. That's all it is. It's a little less strong of a bond, but it's still a bond. So here is what happens with sodium and chloride. If you look at sodium's outer shell, all right, you can count the number of electrons sodium has total. So the inner shell has 2. The next shell has 1, 2, 3, 4, 5, 6, 7, 8. So that shell is full. And look, in its outer shell, it has 1 electron. That's a bad number, okay? That's like having eaten 1 too many donuts and you feel like you're going to puke. So you want to get rid of that donut, and the best way to do it is to give it up. So what sodium does is it says, hey, look, chloride. Here's chlorine, the molecule, and if you look at it, it has 2 electrons in its first shell. It has 1, 2, 3, 4, 5, 6, 7, 8 in its second shell, and then look, 1, 2, 3, 4, 5, 6, 7 electrons in its outer shell. Well, that's just sad. That's the I just need 1 more donut to feel just right. And who comes in and provides that? Sodium gives up its electron, fills the outer shell of chlorine, and turns this into a molecule of chloride. And this is now called an ion. So both sodium and chloride are ions because the chlorine has gained an electron and the sodium has lost an electron. So notice now sodium has a positive charge, a plus, and the chloride has a negative charge because, right, it has the same number of protons in the nuclei of their atoms, but each has either gained or lost an electron. Okay? A positively charged ion is called a cation, and a negatively charged atom is called an anion. Well, it's really about a love story between sodium and chlorine, and how they interact with one another is really, you can almost imagine it in a song. And there just happens to be a song that we can sing. So bear with me while I sing this song. I love this song. Yes, I am a nerd. Here we go. It's a catchy little tune. Sing along with me if you can follow the words on the screen.
Just a little atom of chlorine, valence -1. Swimming through the sea, digging the sea, just having fun. She's not worried about the shape or size of her outside shell. It's fun to ionize just a little atom of Cl with an unfinished shell.
Remember, 7 electrons. She's looking for one more.
But somewhere in this sea lurks handsome sodium with enough electrons on his outside shell plus that extra one. Somewhere in this deep blue sea there's a negative for my extra energy. Yes, somewhere in this form a positive will find a home. Then unsuspected chlorine felt a magnetic pull. She looked down and her outside shell was full. Sodium cried, what a gas be my bride. And I'll change your name from chlorine to chloride. Now the sea evaporates to make the clouds for the rain and snow, leaving their chemical compounds in the absence of H2O. But the crystals that wash upon the shore are happy ones. So if you never thought before, think of the love that you eat when you salt your meat. Think of the love that you eat when you salt your meat.
The original music is from the McGarrigle sisters, a duo of Canadian singers that clearly one of them wanted to be a scientist at some point in her life. Okay, so if you're not appalled by my singing, or even if you are appalled by my singing, I hope that you grasp just a little bit of the difference between covalent, which is sharing, and non-covalent ionic bonds, where, right, one of the atoms gives up an electron and the other one gains an electron. Both of those create bonds, and what is it about bonds that's important? Well, bonds are what are going to link together atoms to create molecules. Life couldn't have happened if we didn't have molecules. And, right, hydrogen, oxygen, nitrogen, and carbon, we link those together, and that creates almost 96% of what's in a cell. So that's a lot of what created the original life form. Going to switch gears a little bit. We'll come back to the other non-covalent bonds, but we need to talk about energy, because understanding how we put together molecules requires that we understand energy. And energy, right, energy, you can think of it as the capacity to do work. There are two kinds of energy. One is called potential energy, and the second is called kinetic energy. There are no other forms of energy. So potential energy is something that can be stored, and it can be stored in bonds. And kinetic energy is the energy of motion. So interestingly, all atoms have electrons, right? So if you have an atom of hydrogen, it has a proton, right? So we'll just make that a positive. And it has an electron, and we always draw it like this, but that electron is never sitting still. You can't know where it is. It's going around the nuclei of the atom as fast as it can. So all atoms have kinetic energy associated with electrons. Electrons have energy, and the energy is associated with that kinetic energy of motion. Really important, the first law of thermodynamics says that energy is conserved. Energy cannot be created. Energy cannot be destroyed. Energy can only be transferred from one form to another, meaning that it can go from potential energy to a kinetic energy to a potential energy. You're going to see there's a lot of different potential energies that we can use, and so you can go from one type of potential energy to a different type of potential energy, and so all of energy is conserved. Well, where did all of the energy that's required for life, where does it come from? If you didn't immediately answer the sun, okay, so the sun, we wouldn't be here without the sun. The sun is what provided all of the energy for creating the macromolecules that began on that early planet life, early planet Earth, all right, to generate life. So how do we talk about energy? Well, energy, this formula at the bottom of this page, Gibbs free energy, will help you begin to understand how the reactions between atoms result in changes in energy. And this is called Gibbs free energy, delta G. Delta G, delta means a change. So, and it's called a delta because it's the Greek letter delta. So, changes in energy and free energy. What is free energy? Well, every single atom has free energy because it's got the electrons that are circling around it. And when you start to put atoms together, it changes the amount of free energy associated with those atoms. So notice we have G is the free energy. We have another delta, delta H, and H stands for enthalpy. Enthalpy has to do with heat, and you can almost not even worry about understanding delta H or enthalpy in these equations because we're going to focus on the last factor here. So the last factor, T, stands for temperature, and in any given reaction the temperature shouldn't change significantly, but delta S is really important, and delta S is the change in entropy. Entropy is how much order or disorder is around in any given reaction. Well, that formula, right, that you should know and learn, right, delta G equals delta H minus T delta S, helps you to understand whether a reaction will occur spontaneously or non-spontaneously. Okay, changes in entropy and changes in entropy, delta S, and changes in enthalpy are what determine what delta G will be for any given reaction. And if delta G is negative, if it's a negative value, it means that a reaction is spontaneous. Okay, I don't expect you to understand that yet, but as I talk through this, I hope that you begin to understand what I'm talking about. Chemical evolution. So if I talk about this in relationship to chemical evolution, what we're talking about is taking atoms, right? We take hydrogen, carbon, oxygen, and nitrogen, and we start making higher order molecules like water, like carbon dioxide, like nitrogen and hydrogen gas. And these are higher order molecules, formaldehyde, cyanide. All of these were generated during the early formation of molecules on Earth. And if you think about this in relationship to delta G, okay, remember I said it's delta H minus T delta S. And, okay, if we just, for the moment, forget about, okay, let's just put a line through here. We're going to forget about enthalpy. Okay, let's forget about that. And we focus on entropy. And you remember I said entropy had to do with disorder. Okay? And is it spontaneous to go from order to disorder? Or is it spontaneous to go from disorder to order? Well, I think you would all agree with me that your houses, your rooms, right? It's so much easier to go from order to disorder, all right, that we could say that that reaction is spontaneous. Okay, think about when you walk in the door, you drop your bag, you put down your stuff, everything is just, right? It started out nice and orderly, but you take off your clothes, you change into something else, and things start to become disordered. And for the disorder to go back to order, what is required? Well, this process here, from disorder to order, you actually have to have an input of energy, and that is non-spontaneous. And the input of energy is required to create that order. So now if I talk about this in relationship to chemical evolution, we have a bunch of atoms hanging out, right? Right, and so they're just hanging out in the atmosphere. Well, they're in a state of disorder, and chemical evolution took those atoms and created some order by making these molecules. And so what we're doing is going from a state of disorder to a state of order. And that required the input of energy. What happens, all right, is that the delta S in this case, disorder, is being decreased. So you're going from a state of disorder to a state of order, and that means you have a negative delta S. And in this equation, if you put in a negative delta S, okay, you have minus T with a negative delta S. Negative, negative makes a positive, and that means that delta G is going to be positive. If a delta G is positive, it means that it is non-spontaneous. Look at this kitchen. This kitchen, somebody was cooking, they were doing all sorts of stuff, everything is all over the place. And how do you go from this state of disorder back to a state of order? Well, you have to put in energy. Okay, you have to actually do work to put everything away. That is not spontaneous. You spontaneously do not do that. It requires energy. So this is a non-spontaneous reaction, which would be a positive delta G. During chemical evolution, all of chemical evolution is saying that we're going from atoms to higher order molecules. Here they're showing you water, carbon monoxide, nitrogen gas, all right? All of these higher ordered molecules, and all of this probably occurred in the early oceans, and with the energy provided by light and heat, we started generating even higher ordered molecules, such as glycine, acetaldehyde, maybe even a ribose. So chemical evolution is our hypothesis to explain what we saw early on the planet Earth. The planet Earth did not have higher ordered molecules, at least we don't believe it did, until over 1 billion years happened, right, before the first living life form occurred. And what was required for that first living life form? It had to have a form of hereditary material. And that hereditary material actually was made up of nucleotides, which contained a ribose, and other molecules that were higher ordered to generate the first living cell. So the hereditary material had to be enclosed in a membrane-bound compartment. So chemical evolution says that the energy from heat and light, which ultimately came from the sun, is what generated these higher order molecules. This is talking about conversion of energy from one form of another. Sunlight, right? Sunlight actually has energy in the form of a wave. That is called a photon. that has kinetic energy. And we have to actually convert that into a form of potential energy in a bond, in a covalent bond, which generates the molecules. So the potential energy of a chemical bond is generated from the kinetic energy that's harvested from a photon of light. So here what they're saying is you have CO2 plus hydrogen plus sunlight, you get higher order molecules. This is chemical evolution. This is non-spontaneous because it requires the input of energy. A significant portion of chemistry is based on redox reactions. Redox reactions are when particular elements are either oxidized or reduced. And there's a way to remember which was which. So one is losing an electron and one is gaining an electron. So loss of an electron, okay, Leo, loss of an electron is oxidation, Leo, and gain of an electron, GE, is Gr. Leo, loss of an electron is oxidation of that particular atom. Gr, gain of an electron, is the reduction of that particular atom. Let's look at this image down below. They're talking about carbon in the methane here. The carbon loses electrons. And how does it lose electrons? So you see that these hydrogens go away. And the carbon, even though it still has shared electrons with it, they're further away than they were before. So this carbon lost those electrons. They're not as close to it as they were. So this carbon is oxidized, whereas this here, these oxygen molecules, this oxygen gets reduced because it gains electrons. Here the electrons are further away from the oxygen than they are in the water molecule. So this oxygen is reduced. So this is Gr, gain of electrons is reduction. Here the carbon atom is oxidized, so that is Leo, loss of electrons. What does this have to do? All of the reactions that occurred in early Earth and continue to occur usually that have importance are loss of electrons, gain of electrons, so they're called redox reactions. Okay, in chemical evolution, this is the same image from the previous page. In chemical evolution, carbon dioxide, so this carbon, all right, its electrons are further away than not because oxygen is electronegative. And this hydrogens, right, the hydrogens share electrons equally. And what happens over here to this oxygen? So the oxygen gets what? So this carbon, does it gain electrons or does it lose electrons? Well, the electrons were further away here. They're still going to be further away with this oxygen molecule. But now electrons are shared equally between carbon and hydrogen. So this carbon actually gained electrons. So Gr. So this carbon is reduced, whereas this oxygen, what happens to the oxygen? Did it lose electrons? Yes, it did. So it is reduced. So we have these redox reactions that occurred early in life. I'm not going to worry too much about these 4 steps of chemical evolution. Don't you worry about it. I want you to understand that early we had atoms that combined together to make building blocks of life, and we're going to talk a lot about what those building blocks are. Amino acids, nucleotides, sugars, lipids. I don't know why it's not on here, but I need to add that. And those building blocks of life allowed for the first organism to occur. And that first organism, remember, it had to be able to replicate. And it replicated itself using energy. Alright, we're going to talk about this experiment in class, but just so you understand, this guy, Stanley Miller, very, very cool guy. He was a graduate student in somebody's lab, and he said, hey, I want to see if I can make chemical evolution occur in the lab. And of course, what did his mentor say? He laughed at him and said, no way, it's not going to work. You can't possibly make this work. So what he did was he generated a setup that he had water in the flask at the bottom of this setup. He added heat by using a Bunsen burner, and what he did was he put just some atoms into the water, and what happens when you heat up water? It steams, so the steam goes into this next chamber where there were gases now, and originally he didn't have these electrodes that are shown, so the electrodes weren't here, and he did this. He thought, okay, heat and atoms, he should be able to see something form. Well, nothing happened when he didn't have electrodes. So he said, well, what was happening in early Earth? There was a lot of electromagnetic energies coming from the sun, so lightning. He said, okay, let's put a spark in here by putting electrodes in. And he did this, right, and he let it go. He let the setup go. And what happens to gases after a certain amount of time? They condense and they'll fall out of solution. And then he did this and he collected them and he let this go round and around and around and around and around. And magically, magic, not really, chemistry happened, and he was able to generate higher ordered molecules, which really gave us concrete evidence that the formation of higher order molecules during early Earth could have happened just the way the chemical evolution hypothesis stated. So that's the end of this lecture. I hope you enjoy it and take notes because there'll be a quiz. So I will see you at our next class.